So, how did we get over that? Okay. It's a very large topic. And we're going to talk about well, literally from A to Z, some pretty basic stuff, things that you deal with every day in your home with your own water supply, and probably most of you from Toledo or maybe other nearby areas still here. But also we'll talk about a little bit of chemistry, a little bit of physics, a little bit of analytical science, a little bit of treatment technology, a little bit of regulations and law. And we're going to have a couple of case studies at the end about topics that you've probably read about over the last few years. And I will say some things that you probably did not read about. And you may find it to be contradictory to what you've read about. But I can tell you it's very well supported, very valid, very well documented. And so, as you can tell, the bottom line point here is really kind of the overall subject. Should you believe everything you see and hear in the press or from the government on water? And the answer, I'll tell you, is no. But the question is, how can you find out? What's the real truth? It's really hard because everything is filtered through the media. So all you know is what they tell us. That's all we know is what they tell us, unless you dig around behind it. And that's not easy always. So anyway, let's see where we go. And oh, by the way, one other thing, I do want you to participate. Don't just sit there. Ask questions, argue with me, whatever. But be involved. Okay. Some basic questions. Is U.S. public drinking water safe to drink? Yes, almost always. The Safe Drinking Water Act passed in 1974. We had no national legislation for drinking water for 200 years. Since then, the federal government has taken the lead role, and then they delegate everything down to the states and beyond. And it has worked very well. This is actually one of those laws that's actually a pretty good law. It works, and we'll see some data on that. How about Toledo area water? Is it safe to drink? Yes, indeed, it is. Is lead in drinking water a risk in Toledo's water? And the answer is generally no. What is the risk of lead in the environment? You've probably read a lot about lead, and in October, 2 weeks before the presidential election, President Biden went to Wisconsin to hold a big press conference to announce this new regulation for lead. That's going to cost $45 billion, by the way. And in my estimation, it's a waste of public money. But we'll talk about that too. So, but where does the lead come from? Why do some children have old lead paint in old houses that are usually low income, where people just don't have the money to do the renovations and the cleanup? And everybody agrees to that. But EPA wrote a regulation that's going to cost $45 billion now to essentially have no benefit, as far as I can tell. Anyway, should you drink bottled water for health? Lots of people drink bottled water because they don't trust their local supply. No, I mean, bottled water is a beverage. If you want to drink it instead of 7-Up or Coke or Pepsi, sure, that's your choice. If you like the taste, by all means. It costs you 1,000 times more than your local tap water, by the way, per liter. So it's your choice, but it's a beverage, no problem. Do you need a home water filter for health? No, your public water supply does a very good job of taking care of what's in the river. And I always tell my class, if you want to drink bottled water, if you want to have a filter in your house, it's your choice. It's not going to do anything for your health, and you're not going to live longer, but it tastes better, okay, why not? This is one of my problems. Okay. What about, should everybody drink the local water? And the answer is no, because there are people in the population who are at unusual risk, who have a significantly depressed immune systems, for example, from the AIDS time. I mean, those people should not drink the water. They should drink boiled water only, not bottled water, boiled water. Should not eat anything raw, should not eat salads or anything like that. So there are people, a few in the population who are at high risk, and they need to do something a little different in their lifestyle. And that's what physicians are for. Physicians should be giving you this kind of advice as to any difference that you need in your lifestyle. Do you need a water softener? Well, the water around here is moderately hard, and as much in the United States, it's at least moderately hard. And so you get a little better lathering with soap if you have a Hope filter that's, a softener. And so again, that's a choice. Washington has moderately hard water. I don't have a water softener. It's just a choice. What if you don't have a water softener? Well, it's going to shorten the life of your hot water heater because you'll get more precipitation of calcium carbonate in the heater, and eventually it'll go maybe in 20 years or so. But if you flush it once a year, that'll take care of that too. What about drinking that water? I'd say bad idea. Don't drink softened water, because what has happened is it's taken out all these desirable minerals like calcium and magnesium. And that's why it's softer. So if you do that, then make sure you eat a good diet that has minerals, maybe even take a vitamin pill, a vitamin mineral pill, so that you get some calcium and magnesium. And in fact, they even sell units now, water softeners, where you can buy a water hardener at the end. But also there's a simple solution, and that is just soften the hot water. Don't soften all of the water in the house, just soften the hot water, which is just a few percent of the water that you use. It means it'll be cheaper, you won't have to reactivate it very frequently, and you'll have all the minerals in the water that you drink. So there are a lot of simple solutions to problems that you didn't know existed. Okay, is the world running out of water? We hear about water shortages all the time. No, it's not. We have about the same amount of water as we had a few million years ago. The problem, it's not where all the people are, necessarily. And there are a lot more people now than there were back then. There are over 8 billion people in the world now. Just in the 1990s, it was about 6 billion. So there's a rapid rise in population, and every one of those people wants a better life. And that means more water consumption, it means more product production, industrial capacity, more showers. And so I think there's a direct proportionality between the water shortages that you read about and the number of people. And great example, Los Angeles, Southern California. They're always short of water. They're always having problems. It's not recent, it's over 100 years ago. They were piping in water from the Owens Valley, which they basically turned into a desert as a result. Now they're bringing water in from 500 miles north of, about 500 miles north above San Francisco. They bring water in from the Colorado River, and they still don't have enough water because of population. People like to live on the coast, they like to live in warm climates. There isn't much water on the coast, usually, other than salt water. And so, again, most of the problems we run into are problems that we cause. It's not nature caused. And again, should you believe everything that you see and hear in the media about water, and maybe about a lot of other stuff too that I don't know about, but I do know about water, and I know you shouldn't believe everything that you read. Okay. Let's see. Okay, so generally, this is a subset of what we do in the course, and I don't think we're going to be able to get to all this we'll try to cover. And I want to prioritize, so I'm sure that we do what you want to hear about, especially in the case studies. Geez. Okay, so we've got algae, which is a local issue from time past. Lead and flint, which is not too far away. PFAS, which is current. Microplastics, which is also another current issue. And even fluoridation, if you want. I don't think we can get through all of these, but I'll do them in the order that you prefer, so that we get as much as possible. Okay, so with this overview, this is the periodic table of elements for all you chemists out there. Why is it up here? Well, I just want to show you that water is a very interesting thing. Hydrogen is the #1 element. It's the smallest element out there, and it's #1. And oxygen is over here, number 6 in that row. That's the 8th overall. But I also did this because I want you to look just below it, and there's sulfur. And sulfur is pretty noxious stuff, but it's pretty similar to oxygen in many respects. And there's a key difference that we'll talk about later that actually makes water so special and so unique. And we'll talk about that. But that's where they are in the periodic table. Why is water such an unusual, special thing? Well, there's a lot of it out there. It's all over the place. You know, the oceans are something like 70% of the Earth's surface. But in addition to the fact it's water, and it's uniquely the basis of life. Without water, there isn't any life in this system of carbon and such that we live in, that we are. And so, but why? What makes it so special? Why isn't there other chemicals that are close enough to water? Well, it's because of the very unique structure of water and its electronic interactions between the oxygens and the hydrogen, and we'll show that. But in addition to all that, it also manages our environment. Why we can live in a relatively limited temperature range with periodic rainfall, and which keeps us all going. That's because of the chemical and physical properties of water also. And for example, the melting point of water, as we know, is 32 Fahrenheit, freezing point also. In Celsius, it's 0, which is just a little more convenient way of naming it, rather than 32, which is kind of an odd number. But, so the melting point is 0 Celsius. Boiling point is 100 Celsius. The density of water is 1 gram per cubic centimeter, and that's the basic unit that's used to apply to all density of all products. So it's that normalizing number that, and the reason water is used because it's so common and because it has these special characteristics. It's a pore solvent, meaning it'll dissolve a lot of things that are ionic, positive charges, negative charges. Not all of them, but a lot of them. Commonly called the universal solvent. It's not really universal, but it dissolves a lot of stuff, including all of our essential chemicals for blood, for body function, for cellular activity. The water characteristics allow all of that to work. Without these special characteristics that we'll get into, none of that would work. The specific heat, well, that's the amount of heat in calories that it takes to raise the temperature 1 degree centigrade, okay? So it's a nice, simple, again, a nice round number, 1, as your normalizing factor. Specific heat, why is that important? Well, to raise the temperature, let's say from 25 to 26, it takes 1 calorie per gram. But if you're at the freezing point of water, at 0, to convert from 0 water to 0 ice at the same temperature, it takes 80 calories. And why is that important? Well, it means when it freezes outside, the temperature doesn't go down as much as it would have because there's heat being released. 80 calories per gram on the lakes and the rivers and so forth. That prevents the temperature from going down too low. It provides a sort of a restriction on the lower boundary. And then the evaporation, we don't go to the boiling point, but the evaporation of water, which also takes a lot of energy, helps to stabilize it in the upper end. And here's where hydrogen sulfide comes in. This is H2S, water is H2O, of course. Sulfur is similar to hydrogen, to oxygen. But hydrogen sulfide is very, very different from water. The boiling point of hydrogen peroxide, hydrogen sulfide is minus 62. The melting point is minus 85. So there's something different about these two things, these two somewhat similar substances. This is the difference. And that's a kind of a simple physical chemical term. It's called hydrogen bonding. And what it means is that you have oxygen, which are the big orange balls, and you have oxygen, which are hydrogen, which is the little one. The oxygen is said to be electronegative. It means that it pulls electrons toward itself, which means that the bonds between the oxygen and the hydrogen are not uniform. They're shifted slightly toward the oxygen, which now means the oxygen is a little more negative and the hydrogen is a little more positive. And so what that means is the hydrogen on one water molecule has an attraction to the oxygen on another molecule of oxygen. And that means in that entire mass of water, the whole glass or the whole ocean, the water molecules are all interacting with each other. They're attaching to each other with weak chemical bonds, but sufficient to change the entire nature of the system. So rather than something that boils at below minus 62, because this is much lighter than hydrogen sulfide, it should boil at a much lower temperature, but it boils at a much higher temperature simply because of this phenomenon. And so it's a very special thing. There's a lot of it around, but it's also very unique, and we wouldn't exist without it. How much is it around? Well, estimates. Worldwide water, 326 million trillion gallons. That's a lot of water. However, 96.5% of it is salt water, either in the oceans or even salty groundwater. It's called brackish water. There's quite a lot in glaciers, relatively speaking, 1.75% in glaciers, but they seem to be melting recently, so that means ocean levels are going to be going up. There's a lot in groundwater. There's actually a lot more groundwater than there is surface fresh water. And even in permafrost, there's some frozen water in the north, in the ground. And a little in the atmosphere, 1,000th of 1% of the total in the atmosphere. Some in lakes and rivers that we can see, but only about 1% of all this is directly accessible water without something that we do. Like, we can take seawater and desalinate it, but if we don't do that, we really can't use it. So since we can desalinate water, we can now create useful water where otherwise it wasn't useful, it was just salty. About 70% of the water that is used in the world is used for agriculture. It's used for irrigation, not for drinking water. And of course, when something happens, everybody goes crazy about the drinking water. When there's a shortfall in Los Angeles, they tell the restaurants, don't provide glasses of water for people in the restaurant. That's absurd. It's such a tiny, tiny amount. It's meaningless. It's for public perception purposes. Be a little concerned about the water. That's what it's about. And of the drinking water that's delivered to your house, only about 1% of it is used for drinking and cooking. The rest of it is washing the car, watering the lawn, and things like that. So we use a very small amount of it, but we wouldn't exist without that small amount. But it also means maybe we need to think of perhaps better ways of delivering drinking water that don't create as large a volume and don't require as much money. Like in Toledo, they treat about 75 million gallons a day. But less than 1% of that is actually drunk. And the rest of it doesn't have to be that pure. And so maybe there's a better way of doing it, something to think about. As you know, water, H2O, and it splits into hydronium. This is H3O, that's a proton added to the H2O to make it a positive acidic molecule. That's what an acid is. And the OH is the hydroxide, which is the basic side. But they're equal. When the water is neutral, there's equal amount of both of those, so the water is neutral. And that's called pH. Neutral pH is 7. Very basic pH, lye is 14. And at the other end, you approach 0 for very strong acidic water. But the only reason for this slide really is to give you an idea of perspective. What does it mean when somebody says there's 1 milligram per liter of this in your water, or 1 microgram per liter, or 1 nanogram per liter, 1 part per trillion? I mean, I think there's a tendency to look at the number and say, oh my gosh, 100, that's a lot. But you have to remember the unit. If it's 100 parts per trillion, that's a 1/10 of a part per billion. And by comparison, 1 grain of salt, 1 single grain of salt weighs about 3 or 4 milligrams. And so if that's dissolved in a liter of water, that means the water contains 3 milligrams per liter of salt. But if you look at this number, there's 100 nanograms per liter. I'm sorry, 1 million nanograms. So 1 part per trillion is 1 millionth of a part per million. So a part per million is fairly small. Part per billion is 1,000 times smaller. Part per trillion is 1,000 times smaller than that. So when you're talking about PFAS, where the standard is now 4 parts per trillion, that means it's the equivalent of 1 salt particle in 1 million liters of water. Give me a break. Okay. Now, there are things that might be toxic at that level, but that's not one of them. And by the way, that I have to mention, there's this fellow who goes by the name Paracelsus, and he was a savant alchemist 500 years ago in Switzerland. And he's now considered to be the father of toxicology, the father of the science of toxicology. He was a physician, among other things, and an alchemist. But the one-liner that makes him famous is, all things are harmful, the dose makes the poison. So if you're not exposed to enough of something, and by the way, even water can kill you if you drink too much water in too short a period of time. So the point is, look at the units and think about dosimetry, dose. How much is too much? And how much is of no significance? Okay, well, this is just some ideas of acidity. What do we know? Well, the water we get at the tap is probably around between, in Toledo, it's probably about pH 9.5 or so, which means it's on the basic stuff. What does that mean? Well, that's okay, no problem. Rainwater is pH 5 and 6. Acid rain is 4 to 5. So it's getting more acidic. Typical river groundwater between 6 and 8, again, sort of neutral, 7 is in between. Bottled water, you can get it acidic, you can get it basic. They advertise that, one or the other will make you healthy, whichever you choose. Soft drinks tend to be around pH 3 because they have phosphoric acid in them. And gastric juice, stomach, pH 1 or 2. So it's really a strong acid in our stomachs. But we're designed to manage that. It works well. That's how we digest our food. A few words about bottled water. There are lots of bottled waters around for sale, we know. There are different sources. Some are wells, some are, I hate these things. Some are springs, some from the river. A lot of the bottled waters, most of the bottled waters that you buy are reprocessed tap water. So basically they take the tap water and put it through maybe ozone, maybe ultraviolet light, maybe reverse osmosis, maybe carbon, and then put it in the bottle. There is such a thing as distilled water that some people drink, which they never should, because distilled water, of course, has nothing in it. It's just water plus bacteria, by the way. So, and the thing you should know that even natural mineral waters, which are expensive and withdrawn from safe aquifers, but they have lots of stuff in them. Natural water has stuff in it. It has minerals, it has ions of various sorts, and it also has bacteria in it. They may be not pathogenic bacteria, but they're bacteria. And no bottled water is sterile. And I'm always amused when I saw that, physicians were recommending to AIDS patients that they drink bottled water. You must be kidding. I mean, the amount of bacteria in a bottle of water keeps going up with time. The longer that sits on the shelf, either in the store or in the warehouse or in your house, the more bacteria have been growing in it and multiply into the thousands or maybe millions. The FDA guidance for bottled water is 10,000 microbes per cc, okay? That's a lot. What's in your public drinking water? Well, maybe a few dozen or a few hundred, maybe. It depends. The simple reason is your public drinking water has a disinfectant residual, whereas the bottled water doesn't. And so bacteria live in water. That's their environment. And even though there's very little nutrient in the bottle, there are bacteria that can acclimate to that and multiply and grow. So it's a function of time and temperature. The longer you keep the water, the longer at room temperature, for example, the more bacteria will be there. They're called opportunistic pathogens, meaning that they're not a problem for almost everybody. However, if somebody is susceptible and there's a very high dosage that they get, they can be made ill. So take your choice. Just a few or a lot. Now, how does the drinking water regulation situation work? Well, EPA writes regulations based on the Safe Drinking Water Act, and then the law also says that FDA should then adjust the acceptable amounts in bottled water relative to the drinking water standards that EPA writes. So within 6 months after EPA publishes a standard, FDA has to make a decision whether that's an issue for bottled water and whether they have to change the number for bottled water. But they're relatively close as they are now. And EPA has 400 people writing drinking water standards. FDA has 1/3 of a person producing bottled water guidelines. One of them is at an extreme. I'm not sure which. Okay, well, a little more about bottled water. Before the Safe Drinking Water Act was written in 1974, virtually nobody in the United States drank bottled water. It was, well, that's Europe. You can't trust the water in Europe after the Second World War. There was all this destruction. And so lots of people in Europe today still drink bottled water routinely. Well, also now a lot in the United States, and the numbers keep going up after the Safe Drinking Water Act was written, when the water got safer. And so you have to say, what's going on here? Well, as of 2020, I saw that statistic, half a liter per person per day. So that's 330 million people. That's 165 million liters per day of bottled water. That's a lot of water. And it's expensive water too. And the cost, as I said before, is about 1,000 times tap water cost on a unit basis, liter to liter. Why would people drink bottled water? Well, if you don't like the taste, okay. As I say, it's a beverage. If you don't like the taste, okay, drink something else. Or you can get a $20 little filter and screw it onto your tap, and that'll take out the chlorine taste, which is what you're mostly tasting. It'll take it out for several years, and it's very cheap. Again, if that's your only concern, the taste. Some people don't trust the local tap water. They think, well, I don't know, was it safe? Maybe not. But you really should. It's heavily regulated, and there are just a relatively small number of places in the country where you can't trust the bottle of tap water, and that's usually a small community somewhere where they don't have any people to run a water plant. They don't treat the water. They just pump it out of the ground, and most of the time it's okay, but sometimes it isn't. So, but if you're in a municipality like here, you have lots of engineers and others who are processing the water, treating it, purifying it, and delivering it. It works almost everywhere in the world in the developed countries. Canada, US, Japan, Europe. You can trust the water. A lot of other places you can't. So don't drink the water if you're traveling in Uruguay maybe, or someplace too. However, bottled water is valuable in the case of emergencies, floods, et cetera, et cetera. Truckloads of bottled water are brought in, and it allows people to survive until the public system is put back in place.
Dr. Drew?
But even though it's in a bottle and it's treated, just one second, there actually have been disease outbreaks from bottled waters. So, nothing's perfect. Okay, go ahead. Yes?
On that topic, then, local drinking water and things, when they issue a boil advisory,
Yeah.
what does that really mean for us? Because not everybody gets that, obviously, he keeps drinking out of their tap.
Well, boil water advisories are both important and controversial because, first of all, the public water system is very risk averse. If something goes off a little bit, they may issue a boil water advisory, not necessarily for the whole city, it may be for some particular area, because they don't want to take a chance. Most of the time, it's not really necessary because there isn't a risk. For example, one of the reasons they commonly issue a boil water advisory is if the pressure goes down a little bit in some part of the community. And that can happen. I mean, what if you have a fire and they're pumping water out, thousands of gallons, and so that reduces the pressure in the system. Well, what that means is it's possible, since the pressure is now less in the pipe, that it's possible if there is some opening, a hole in the pipe, that water can seep in. And so when there's pressure in the line, it can't because the water is pushing out. So in the interest of caution, frequently, Washington, for example, they've issued a number of boil water notices, just for that reason, because the pressure dropped briefly. However, World Health Organization says, be really careful when you do that, because boil water advisories are really disruptive. They cause people to choose different sources. So you better, be sure that you really do have a potential risk. Don't just issue a order at the drop of a hat, kind of thing. But again, water suppliers are risk averse, and so they don't want to take the chance. And so you probably have more advisories than necessary. there, could you hold your hand up there? Okay. Okay, microbes. As I said, the water is not sterile. The tap water isn't sterile, bottled water is not sterile. And so this is just look at the colors here, don't worry about it. But this is a study that was done a couple of years ago in Maryland, at the University of Maryland, in fact. And each of these columns is distribution of bacteria detected in water samples that they collected. And the list is on the right, I can't even read them, but so don't worry about it. But each color represents some different organism. These three are bottled waters. This one is natural mineral water, which is a premium thing, you know? And so, you know, they've all got stuff in them. And one of these is a water fountain, and the other one is a tap and such. So the point is pretty simple. There are bacteria in water. Most of them are not harmful. If they are harmful, then you've got a real problem. And that, in fact, is the great public health renaissance of the 20th century. It wasn't until about 1907 where the public health officer in New Jersey, might have been Jersey City, New Jersey, thought, you know, they had their running waterborne diseases, you know, typhoid and other, and he thought, well, gee, we ought to do something to try to kill those things in the water. Let's add chlorine, which hadn't been done before. Well, of course, there were lawsuits and all sorts of arguments in the community. Well, eventually, the judge made the right decision and said, yes, you're allowed to chlorinate the water. And son of a gun, waterborne disease rates dove down. So with that combination, and then many other communities began to pick it up too. So with the combination of chlorination, which is cheap and simple, and filtration, which is also pretty cheap and simple, basically sand filtration, which is very commonly practiced all over the world, essentially eliminated pathogenic waterborne diseases. About 1907 to the 1920s, Cincinnati, by the way, if you lived in Cincinnati, and you were a child born, there was about a 25% chance that you would die before age 2 because of sanitation problems, partly due to waterborne disease, partly because Cincinnati is on the Ohio River, and you know there was sewage coming down the river from Pittsburgh and everybody else. So the point is, it's a very different world that we live in now, and it's better than it was, regardless of what somebody might tell you. It's a whole lot safer than it was. We've virtually eliminated those kinds of infectious waterborne diseases now, except if somebody makes a blunder, which can happen occasionally, but very, very occasionally. Well, just very quickly, we're at 9:45. I'm gonna just say a few words here and then flip over to the case studies, so we'll be sure to get into those. But just so you know, there is a Safe Drinking Water Act. It's very comprehensive. It covered, this is from 1974. There are 150,000 public water systems in the United States. That means everybody. That means campgrounds and the whole works. Interstate highway, McDonald's, considered a public water system if they have their own well. 50,000 community water systems where people live, and they're defined as at least 25 people, 15 connections. So that means most of the country, about 90% of the country, is covered by public water of some sort. The other 10% are people who have their own wells. And many times that's good, fine, but times it may not be, because they're basically drinking the water that they find. They're not in a position to treat it, to upgrade it, unless maybe some salesman comes and sells them a $10,000 water treatment unit, which then, you know, then you have to pay that person forever to come periodically and look at it. Okay, well, most people don't need anything like that. But Nevertheless, there's no control at all on those. And so if you happen to have a septic tank that's, not far enough away from the well, you can be contaminating the well and your drinking water. So it's a good thing to have a public water system because somebody's taking care of you. Let's skip. Okay, I do want to show you this. Waterborne disease outbreaks. Centers for Disease Control keeps track of reported waterborne disease events that occur in the country. This starts at about 1972 or so. But if you went back a few decades, the numbers would be way higher, much, much higher. But here, what is interesting, I think, is that this is around 1980. And this is when the new regulations went into effect, when water supplies, all water supplies were then required to do monitoring and put in treatment, and if they have a problem, report it and fix it, okay? So this was kind of a peak time, and then the numbers went down very nicely. By the way, waterborne disease outbreak is hard to detect, but it's also defined as 2 or more cases of disease in a location that can be attributed to the water. And so it has to be shown to be related to the water. For example, identical bacteria or viruses, whatever. Well, okay, so you see it went down nicely, but then the numbers started going up. The reason they went up was because of this dark area, because this is now a new disease. So this is legionellosis. This is the disease that grows in your plumbing. These are the microbes that grow in the shower head or whatever. And it was only identified in 1976 in Philadelphia at the Legionnaires' Convention, when I think about 25 people died and about hundreds were made ill. Not from the drinking water though, but from the air conditioning system. Because what happened was, air was being circulated through the hotel up to the heat exchanger on the roof, which cooled that. But as it was cooling, the water temperature went up. And as the temperature warmed up, the Legionella grew. And then they were blown out in the vapors, and there was an air intake not far away, and they were sucked into the air intake for the hotel, back into the hotel. And so all these hundreds of people were made ill. This bacterium had never been seen before. It took CDC about a year to identify it, and they finally did. But nowadays, as far as I can tell, it's the only waterborne disease that kills people. And it's not from drinking the water, it's from inhaling droplets and aerosols, such as taking a shower. So, is there a concern in your house? Probably not, because if you're taking a shower every day or so, or every other day or something, the water is purging out. It's flushing out. But if you go to a hotel and maybe that room hasn't been occupied for a week, you should flush that shower before you get into it. Turn it on, close the shower curtain, let it run for a little bit, then get in. So this is, EPA's done essentially nothing about this. As I say, it's the only disease that's linked to water, pretty much, that we know of today. And there's no such thing as typhoid, cholera, et cetera, they're all gone. So, okay. A couple words about Toledo, of course. Maumee Bay, Maumee River, Lake Erie. Generally, I think they put out about 75 or 80 million gallons per day. The commissioners here today, and they store about 75 million gallons of it a day. And every water supply is required to put out what's called Consumer Confidence Report, which is supposed to tell you annually Is there a problem? Did we fix it? And when will we fix it, and so forth. It's to keep you informed. It's one of the unique parts of the Safe Drinking Water Act. It basically puts the responsibility on the water supplier to let you know if they're having problems. First of all, so you'll know, but secondly, so you'll then support them for the improvements that may be necessary. Okay? So, unique and very effective law, I think. But you have to read the thing. You know, it's online. Essentially every year they're required to put one out. You have to go online and look for it and read it. It's half a dozen pages maybe. Lead is an issue everywhere. Is it an issue here? No. It's the treatment that they provide keeps the lead levels far below the action level that's specified in the regulations. They add a little fluoride to the water, which is controversial these days now, all over the country. The hardness is in the moderate category, about 80 to 90 milligrams per liter. And it's recorded as calcium carbonate, but it includes magnesium carbonate, et cetera, et cetera. And they haven't detected PFAS in their source water, so that's good news. They have what's called conventional treatment process, filtration, sedimentation, coagulation, we won't go into that, but they've spent about $500 million in the last few years as a follow-up to the algae problem of years ago. I have my doubts whether 500 million was necessary, but that's another story. I think it was ordered by the state pretty much. And it was, I've heard the story, by the way, that the governor actually had a conference call with the city and said, you will do this, you will put on the ozone, you will. And the governor must be a real water treatment expert, I guess. What to do. Anyway, so it's very highly treated. It's one of the best treatments in the whole country these days. Okay, well, let's do some of these. Let's start with, do you like algae for starters? Okay. Do you remember what happened? Well, okay. So the issue is that, first of all, algae growths and proliferation are very common. They're everywhere. They're climate related and they're nutrient related. It means if the temperature warms up, as it always does in the summer in northern climates, and if there's sunshine, and if the water is kind of slow moving, it doesn't flow like a river rapidly, and if the water is not real deep, such as Western Lake Erie, you're going to have an algae bloom. And sometimes they're very extensive and sometimes not so much. But when I lived here, I remember every August you could taste a little something in the water, and it was because of the annual algae bloom. Well, you had a big one a few years ago. The culprit is called cyanobacteria. Has nothing to do with cyanide, by the way. It's the color, cyan, blue-green. That's where it got the name. And you know when you've got one, a bloom, from the water turning green, from the particles, from the taste. And Western Lake Erie, since the Ice Age, has been what's called mesotrophic, which means it's kind of on the borderline to being able to create some of these conditions and therefore algal blooms and other problems. And Tom Richmond, Professor Richmond, who might be here, runs the Toledo Lake Erie Center, which keeps track of this and other things associated. Well, this is what it looks like. This is a kind of blurry. This is a satellite photograph from 250 miles up. And you can see what it was like. This is Lake St. Clair, Detroit River, Toledo is here, Sandusky, Cleveland, and so forth. So you can see it was a massive bloom covering all of this area. And in fact, it was a little worse over here than it was in Golden Bay, at least when this picture was taken. So as I say, Lake Erie has been prone to this kind of thing for about 10,000 years. Where do the nutrients come from? They typically come from agriculture, from runoff, from the fertilizer, the nitrogen and phosphorus that's added in this agricultural area and upriver, and it flows river and downriver if you need to this area, and therefore upsets the nutrient load and triggers the bloom. Well, here's one of Tom's pictures. This is the water intake in Maumee Bay, Port Toledo, and this is some water that they pulled out, and so you can see there was plenty of stuff floating in it that they had to take out. So as I said, it's seasonal, warm weather, sunny, slow moving water, shallow, nutrients, sunlight. And frequently what you notice quickly is the taste of litter that's contributed. And nowadays, though, the treatment process they're using pretty much gets everything down to low detection. So it's very well covered. This is what the chemical looks like, yes?
I wanted to know, how does turbidity influence algal blooms?
How does what?
Turbidity, turbidity.
Oh, okay. Well, the question was, how does turbidity influence the algal bloom? It's twofold. On the one hand, if the water is turbid, there isn't much sun penetration, so you don't get much of a bloom. On the other hand, once you produce the bloom, you saw how much there was suspended in the water, and so you get turbidity added. So it's two different kinds of turbidity with different results. All right, this is called microsystem LR, in case you were curious. It's called a polypeptide, meaning it's got a lot of amino acids in it, plus some other things. And the interesting thing as a chemist, if you looked at this molecule, you'd say, and your question was, well, how can I denature it? How can I detoxify it in a water plant? And this little thing right there, this, right there, those two double bonds, it's called a conjugated double bond. It's chemically very reactive. And so if you chlorinate this water with free chlorine, that's HOCl, hypochlorous acid is what you need. It'll react with this very quickly and knock it out. And so my guess is during the time of the bloom in Toledo, they were chlorinating, but they didn't have hypochlorous acid because the pH is about 9.5, and so you're not going to have acid present at that point. You have hypochlorite, which is a disinfectant, but it doesn't react with this double bond. So if they had, for whatever, were able to run at a lower pH, or was able to let that water be stored for a much longer time, eventually the small amount of chlorine that was present would have reacted with this and knocked it out. So chemistry is important when you deal with, for engineering, you need to know what technology to use based on what the problem is and what the choices are to fix it. Now, they closed down the water supply. They said, don't touch it, don't drink it, don't wash the dishes, don't take a shower. Everybody went off and bought bottled water. Based on the state directive, which was 1 microgram per liter was the trigger. Now, 0.95 wasn't the trigger, 1.0 was the trigger. So tell me, as a toxicologist, was there any difference between 0.95 and 1? Of course not. But in their infinite wisdom, the state said, you will tell people, don't drink the water, don't touch the water, don't wash dishes, don't take a shower. Well, that lasted for a day or so, and then they got the numbers back down, and so it was all reversed. However, the damage had been done. The community was disrupted totally. Bottled water disappeared from the shelves. I found out that it was a tactic that the state used to force the city to put in, to do some upgrading and operation and maintenance and improve the treatment process. rather than say, well, you know, you're out of compliance with this, and so, we want you to, you know, whatever, put in a new roof or whatever it is, and do the normal legal process, they didn't do that. Why not? Well, probably for politics, because it's embarrassing, it's difficult. If you have the same political administration in the state and in the city, it's very embarrassing to the party if something is made negative about the local politicians. So rather than go through the straightforward, direct, simple approach, they waited for this and used this as the excuse to force all of the activity, okay? Now, was, you know, 1 part per billion, okay? It's not good for you, but it's okay for the short term. They used 1 part per billion as the guideline. And I called the water director in Columbus and I said, well, where did you get that 1 part per billion? And he said, oh, well, that's the WHO guideline. And I said, no, it isn't. I'm on the WHO committee that produced that guideline. That's the lifetime guideline. That's if you're drinking water for 70 years every day. That's not 1 day. Oh, yes, we knew that, he says. And I said, well, did you explain that to the community that, you know, this wasn't really an emergency? It was something that needed to be fixed. Well, no, we didn't do that. I mean, that's not the way it's supposed to work, you know. The people that are administrators and so forth are supposed to be honest. They're supposed to tell you the truth. So, even so the 1 for 1 day compared to 1 for 70 years, okay, you know, it's absurd. And EPA then had a guideline that they put out, which was 0.3 for young children and 1.6 for adults for 10 days. Also wrong, because they used the wrong study to produce it. WHO's number was 12. They used a study that was carefully managed, well recorded, high doses of exposure to the animals, 1,000 safety factor put on the result from no effect. And they came up with 12 for short-term exposure. No problem. EPA used a study that was conducted in East Germany in a laboratory that produced their own rats of unknown history, no data in the literature that says, you know, these rats are susceptible to this and to that and to that, whereas the studies that are used for normal are a set of rats that are commercially available. Everybody uses them. There's a huge literature on what they are affected by and doses and all that. Not at all. So he picked this one because it got a lower number. Come on. So